Cool. Welcome to Lecture 6 of Vector101. We're going to continue talking about linear transformations and matrices today. And as always, I'm going to remind you, number one, doing the exercises is extremely important to learning the content. So you should do them. And then number two, we have office hours on Saturday. They're on every Saturday. They're at 1 p.m. Pacific time. And this is a 1 hour time where you can come to ask Aiden and I questions about the course. And I just realized I don't have the chat open. Let me get that up. Okay. I see all the messages now. All right. Cool. And then what are we doing today? Well, we're going to start off by recapping some stuff about linear transformations. And then we're going to explore some demos of linear transformations and see what they look like. See what some of them look like anyway. And then I got a little bit ambitious. I think we're axing number 3. And then the fourth thing we're going to do is that we're going to start coding a matrix object. And we won't finish this today, but we'll start. Okay, so the first thing we talked about on Monday was functions. And as programmers, you already understand what a function is. We just, as mathematicians, write them a little bit differently. So a function is a machine, and it eats elements from one set, and it spits out elements to another set. So here, this function f, it eats elements from x, and it maps them to a unique element in y. Like, this is all a function is. It's like, no longer are we considering a function to be like just some curve on a plane. Like, this is a function, but it's not the general definition of a function, right? So we're not doing this anymore. A function just takes in elements from one set and it spits out elements into another set. And we have a special notation for this. We say that first we give the name of the function. So we say f, this is our function, and it eats elements from x and it spits out into y. So this is the name of the function, and then this is x is the set it eats from, and then y is the set it spits out into. So we tell the reader, like, okay, this is generally what my function is. And then we have to tell them what our function is actually doing. So we have to give the rule for what the function does. So we take in x from this set, and then we specify a rule that returns a value in y. And if this looks scary, it really shouldn't, because we do this all the time in code. So on the left here is how we would notate a function mathematically. So again, the name of the function is f, it eats from x and spits out into y, and then has a rule that it takes in x and it squares it. But then in code, we do pretty much the exact same thing. So over here, we name the function f, and we say that x is of type x, and it spits out an object of type y, and then we give the rule. So there's a subtle difference where, like, on the left in math, x and y are sets, and on the right in the code, x and y are types. But it's the same idea, really. And, I have another example here, but it's the same idea, right? Proj is the name of the function. It eats 2 vectors and spits out a vector. Proj is the name of the function. It eats 2 vectors and spits out a vector, right? So this is all of this notation is saying. And then in this course, in linear algebra, there's one type of function that we really, really like. So foremost, the functions that we're talking about take in vectors and they spit out vectors. So we say that they're vector valued. And the functions that we care about are also we call them linear transformations because they satisfy this property. And this is a lot to take in, I think. So I'm just going to highlight for you what's happening. So T, our linear transformation, is taking in a linear combination. So these are vectors. These are vectors scaled by scalars, and then we sum them up. And what happens is we look at the scalars, and the scalars end up out front. And then we look at the vectors, and the vectors stay inside. So what we say is that T distributes over linear combinations. So we take in a linear combination, and then the sum on the inside comes out to be sums on the outside, and then all of the scalars end up out front. So this is a linear transformation, and it's functions that this is what linear algebra studies. And, Aiden on Monday made a really big deal about how important linear transformations are. So like, I'm not going to list all of their applications again, but like, these are extremely important. These are like the most important functions in all of applied mathematics. So this is the same thing that I had on the last slide. And what you show in your homework is a challenge question, is that this definition here, this to me kind of scary looking definition, is actually equivalent to what I think is a little bit simpler definition to parse. And so if a function is linear, then it also satisfies the following two properties. So if we take in a scalar times a vector, we get this. And then if we add two vectors, t of x plus y, it becomes t of x plus t of y. So if a function is linear, if this is true, then necessarily this is also true. And conversely, if these are true, then this is also true. So these are equivalent definitions. So you can, well, first you should show it, but then you can choose whichever one you like. All right, so now we're going to take a break from the math and we're going to look at some linear transformations. Okay, so here we are in Studio. Let me linear this one. Okay. So here in Studio, I have a part, and each of these vectors is pointing towards a corner of the part. So what we're going to do is we're going to apply some linear transformations to the part, and we're going to see what happens. And to be clear, a part is not a mathematical object. We're not like we are applying the function to the corners of the part. We're not applying the functions to the part. Okay, just like a important difference. So our first example of a linear transformation is a uniform scaling. So if let me make this, let me do that. All right, so if I scale this part, what I'm doing is I'm scaling each of the corners by the same constant. And so this is a linear transformation. And like, I'm not proving to you as a linear transformation, we're going to get there, but we're just looking at some examples. So this is our first example of a linear transformation. It's a uniform scaling. We can also scale non-uniformly. So if we scale non-uniformly, this is also a linear transformation. So we can stretch along, we can stretch along one direction, stretch along the other. And then lastly, the last one I'll show you, I mean, there's plenty more, but just the last one I'll show you is rotation. Rotation is a linear transformation. And what I'm doing right now is I'm just applying the transformation to the corners. But I could also apply it to the entire space. Let me reset here. So we can think of the linear transformation as affecting the entire space. So we are scaling all of R3. We can stretch it. Oh no. We can stretch it. And we can also rotate our entire space. Okay, so I thought that was fun. But yeah, so these are some examples of linear transformations that we can do in Roblox. And specifically, these are transformations that take 3D vectors and spit out 3D vectors. But but there are linear transformations that map vectors from one dimension to vectors of another dimension. It doesn't have to be from 3 to 3. All right, so those are just some examples, and now we're going to talk more about why they are linear transformations. Okay, so these are the transformations that we just saw. We saw uniform scaling. So this takes in a 3D vector and it spits out a 3D vector. And what we do is we just scale every vector by the same constant. And then we also saw non-uniform scaling. We saw rotation. But there's an issue, which is how do we write these down? Like, what is the formula for rotating a vector? What is the formula for non-uniformly scaling? Like, these are hard. And in some cases, you can't even write down your linear transformation. Like, it's literally impossible. So we need some way, some better way of writing down our linear transformations. This might be a little ambitious. What I had wanted to do was prove that uniform scaling is linear. And I'm looking at the clock. What do I have next? I think we'll have time. Okay, so I'm going to prove to you, at least for one of these, why they are linear. And hopefully this will also help you out with your homework because you have some similar homework exercises. So let's recall that given a linear transformation, given a transformation, we want to show that it's linear. How do we do this? Well, first we show that t of alpha x is alpha t of x, and that t of x plus y is t of x plus t of y. So we're going to show both of these. So we'll start out our proof. We'll say, all right, given a linear transformation, t from R3 to R3, such that, and we'll give our rule for our function. So the rule of our function is that we take in a vector and we scale it by some constant. Then, so now we're going to prove our two properties. So first we'll start with the first one. So if we scale x by some constant beta, then what happens? I guess just by definition of linearity, really. But okay, so like what does t do? T does this. T takes the vector we're putting in and it scales it by alpha. And then these alpha and beta, these are just constants. So we can switch their order. And then look at this. This is just beta t of x. So good. We have our first property. And then second, so now we'll put in two vectors, t of x plus y. And again, what does t do? It scales by alpha. And then if you did your first homework, you know that alpha distributes. So now we have alpha x plus alpha y, and then this is just t of x plus t of y. So t is a linear transformation. Okay, so hopefully now, well, maybe you already believed me, but now we're like really sure that this uniform scaling is a linear transformation. Okay. But then there's the issue of the other two. Like, well, I in this case I knew what the function did, and so because I knew this, I could show these two properties. But like, what if we have these two functions? Like, how do I prove that they're linear transformations? Like, we need some better way to write them down. So how do we write down a linear transformation? The answer to this, I'll just tell you, is that we look at where the standard basis vectors go. And this is like really important. And this is actually not a fact that I understood myself until far too recently. This is really important. Like this is how we write down a linear transformation. So what do I mean by this? Let's recall what the standard basis vectors are. They're these E vectors. So E1, this is a 1 in the first coordinate. E2 is a 1 in the second coordinate, and so on. So given these standard basis vectors, we can write down some vector as a linear combination of the standard basis vectors, right? Because if we scale E1 by x1, this just becomes x1 in the first coordinate. If we scale E2 by x2, this just becomes x2, right? And so on. And then when we sum them all, you should just get x. All right, and then what do we do with this? Well, now, so I'll zoom in here. So now we're going to put this into our linear transformation. So we'll take x, and we know now that we can write it as a linear combination of these standard basis vectors. And then by definition of linearity, this pops out. Because remember, t distributes over the linear combination. And then we're just going to redefine these. So we're just going to just give them names. Like t1, we're just going to, this is the name of t of e1. And t of en, we'll give it the name tn. And then the last thing we'll do is we'll just give this its own notation. So we're going to put t1 as a column vector here, and tn as a column here. And together they make a matrix. So, okay, what do we do? So we wrote x down in the standard basis. We then applied linearity by distributing t over the linear combination. And then we just gave these guys names, these t1 through tn. And then lastly, we just gave it a notation. Like that's all this is, that's all a matrix is. It's just a notation for linear transformations. So, right, so the upshot is a matrix represents a linear transformation. And furthermore, a linear transformation sends the standard basis vectors to the columns of the matrix. Right, so this is how you arrive at a matrix. We apply t to the standard basis vectors, and then we end up with these columns. All right. So now, armed with this information, we're going to again look at our linear transformations in Roblox and see if we've learned anything. Okay, so this time, what I'm doing something a little bit different. So these red, green, and blue, these are the standard basis vectors. But I'm also like using them as the up, right, and look vector of this part. So this part is just meant to like visualize what's happening to this space. Okay, and so let's remember like the standard basis vectors get mapped to the columns of our matrix. And the columns of our matrix, like, how do I say this? It's hard without the tablet. Like we need the columns of our matrix to Oh, I'm at a loss for words here, right? But like the point is that the columns of our matrix like tell us what happens to what the linear transformation is doing. And okay, I'll just show you the demo now. So we're going to, in this case, we're going to take this blue standard basis vector, and what our matrix is going to do is it's just going to stretch it out. So this is like the first column of our matrix. We took the standard basis vector and we like multiplied it by 2 or something. And this is what it does to our space. So it stretches out our space. Sorry, I'm missing with my trackpad. Okay. And similarly, we can do this for our other axes. So we can scale our axes, and we can do a little bit more than this. So we've seen already that rotation is a linear transformation. And with the rotation, you just rotate the standard basis vectors. All right. But we can do a little bit more. So we saw scaling, we saw rotation, but now that we can just freely move around our basis vectors, we can do a little bit more. So for instance, we can skew our part. Right, this is a linear transformation. And, well, let's see, what else can we do? We can also invert our part, and, well, it doesn't look like anything happened, but I'll show you, in Roblox, you actually can invert a part. So this is what happens if you invert a part in Roblox. Right, okay, so like what's the point? The point is, to define a linear transformation, all we have to do is define where the basis vectors go. All I've done is I've taken these 3 standard basis vectors, I have moved them a little bit, and that's my function. Sorry, changing back now. Okay, well, I should stop here for questions. Anybody have questions about the demo that I just showed, or anything about how we arrive at matrices from linear transformations? All right. So we'll keep moving on. What else can we do with matrices? So we've seen this first one. So for function evaluation, so given some linear transformation t, evaluating t is the same thing as taking a matrix and multiplying it by a vector. This is what we saw on the last page here. T of x ends up being, in our notation, just multiplying a vector, multiplying a matrix by a vector. And what else can we do with matrices? Well, function composition, where we put something into a linear transformation, and then we take this and put it into another linear transformation. This works out to just be matrix multiplication. And we can do other things, so we can add linear transformations, and this is just adding matrices. And then we can scale a linear transformation, and this is just scaling the matrix. So like the point is that we want to do something with a linear transformation, but writing this down is hard. So we represent a linear transformation with a matrix, and now we can write it down. This is like, if you have one takeaway from this lecture, it's that matrices represent linear transformations. And I should add that like this is not, I'm just like telling you how this works, how you get from one to the other. You should really prove this, and I might actually sign that for homework. Like proving how you want to do addition of linear transformations, and it works out being addition of matrices. But for today, just for lecture, we're going to go with this so that we can start coding our matrix object. All right. The last thing I have here is just some notation that we have started accumulating. I know it can be a lot. Yeah, math notation can be really frustrating. Like the field that I prefer is called differential geometry. And in differential geometry, there are like 5 competing notations for every single thing. And it makes reading any paper, any book, a huge pain because you have to like mentally switch between the notations. So I get it, and I just wanted to compile for you what I think is like most of the notations that we've seen so far. And there's a second page for it too. So you can save this for yourself, look at it on your own time. Hopefully this is helpful. I'm glad you screenshotted it, Neptune. Okay. All right, so we have started at linear transformations. We have represented them as matrices. We know that matrices or linear transformations take the standard basis vectors to the columns of the matrix. Now we are going to code a matrix object. Okay. All right. I hope this was like an informative demo. I thought this was really neat. Oh, and by the way, it's magic. They're just wedges. They're not. It's not a part. It would be cool if you could skew a part in Roblox. Okay, I see that I've fooled some people. I guess Neptune, you could skew a part if it was like rigged with bones, but whatever. All right. Oh no, you're not supposed to see that. We're coding a new matrix object. Okay. As with any object ever in Roblox, we're just going to start with some boilerplate. So we're going to define our matrix class, and we're going to need a constructor for a matrix. And our constructor is going to take in a grid of numbers. So maybe we'll just call it grid. And here's how we, oh, it didn't like that. Here's how we would type, like static type this, which is that we have a list of lists of numbers. And so the format of our matrix is going to be like this. So first we're going to have an outer table. So maybe we'll give it a name. So matrix A, and then each of the lists on the inside is going to be a row. So this is going to be A11, A12, and so on through A1n. And then, so dot, 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 and then at the end, it's going to be AM1, AM2 through AMN. So these are the rows of the matrix. All right. You could do some type checking on this. It's like obnoxious, and I'm just not going to do it, at least not in lecture. All we're going to do is we're just going to say matrix is we're just going to clone the grid, and we're going to like hope that the user put in the right things, but on your own you can feel free to add some asserts here. Sorry, I missed a question in the chat. Neptune says, could you not deform a part as you could the camera? No. Is that right? I don't think you can. I think you could try. I don't think it will let you. Yeah, okay. JMK confirms it doesn't let you. All right. Right, we're creating a matrix, and we've copied our matrix, and now we're going to, well, we're going to need how many rows are in the matrix, so why don't we store that? So the number of rows, remember that the rows are the inner tables, so it's going to be the number of those inner tables. So it's going to be the number of lists in the grid, and then the columns is going to be the dimensions of these vectors. So it's going to be the number of grid one. So we're going to just take the first element and we'll get its length. That's going to be how many columns we have. And then lastly, we'll return the new matrix, and we're going to set its meta table to matrix, which is not something we've done before, by the way. So in the past, what we did was we defined a new meta table for matrix, a standalone meta table. But convention on Roblox is to just use the class as the meta table. So it's like kind of a hack, I guess. So okay, so like here's what I mean. So if we wanted to do some operation like okay, right. So we wanted to do some operation like matrix add. We want to do this on some table. Well, the table obviously does not have the add function. So then it goes to its meta table and it says, hey, meta table, where should I look for the add function? And the meta table says, oh, you should just look in me. And then, oh, sure enough, it's there. So it's like classic meta table indirection, and it's really hard to follow, but like this is the standard that Roblox has, and so I'm just going to keep with it. Sorry, checking the chat. Okay, so what next should we do for our matrix? Well, certainly we're going to need to be able to add matrices. So we'll do that. And we're going to take in a matrix A and a matrix B, and we should probably type check, well, do a small bit of checking that hopefully what the user gave us really is a matrix. So let's have some like is matrix check. And we'll just, we'll return if the meta table of the matrix is indeed the correct meta table. So we'll say, all right, so we'll assert that A is a matrix. We'll assert that B is a matrix. And then importantly, we can only add vectors of the same dimension. So we should also assert that the rows of A are equal to the rows of B, and we'll assert that the columns of A are equal to the columns of B. Finally, now we can do our add. So we'll need some empty matrix. How are we going to make an empty matrix? Yeah, so this is kind of obnoxious, and I guess the way that I've solved this in my code is to add a new method, matrix.empty, a new constructor. So what I'm saying is that if we want to add these new matrices, we need somewhere to put the additions, right? So we need an empty matrix, and so we'll just make a new constructor for that. So we'll create a new table that can hold all of our rows, and then for each of our rows, we're going to make a new table, and this one is going to be the length of our columns. Aiden, you're worrying me. Okay, so now we can just create a new an empty matrix. And then the way that we're going to add them is that for each of our rows and for each of our columns, the ijth entry of the matrix is going to be the sum of the ijth entry of A plus the ijth entry of B, something like that. And then we'll return our new matrix. Before I move on, is this clear what I'm doing? Because the rest will not make sense if it's not clear. So all we're doing is we're just looping through each of these coordinates for the two matrices and just adding them together. Okay, good. All right. Next low-hanging fruit is subtraction because it's like the same thing. So we'll just copy this, paste it, and change the plus to a minus. There we go. Another low-hanging fruit is negation. So negation is really like multiplying a vector by -1. We'll take in our matrix and we'll do something similar. Right, so we should probably check that our matrix is a matrix. And we'll take this. Uh-oh, I renamed it. I guess I had to call this new matrix. And so all we do is we just negate the ijth entry of our matrix. And then return a new matrix. Thanks for that. Okay. These are the easy ones. Well, I guess really say we're only implementing the easy ones because next week we'll do matrix multiplication, but we need like some base to start with. So we're just doing these. All right, so we have addition, subtraction, negation. Next we can do scalar multiplication. So there's two cases here. We can either multiply a matrix on the left by scalar or on the right by scalar. Now usually, like anytime I've ever written matrix scalar multiplication, I always write the scalar on the left, but like in code, I mean, even in the math, you could put the scalar on either side, but so we'll do that. So in the first case, check if A is a matrix and B is a number. In the second case, we'll check if A is a number and B is a matrix. And they're going to be very similar. What did I do over here? Oh, else if. There we go. So again, we're going to need some new matrix, so some empty matrix. Going to be the size of the rows of A and the columns of B. And then we're going to loop through each element. So for each row in... Am I doing this right? Yeah, for each row in the matrix, and then for each element in the row, we're going to set the ijth entry of the matrix to be our scalar times the ijth entry of A. And then we'll return a new matrix. And then similarly, this is the exact same thing, except A and B have switched roles. And I should point something out. So usually like in Luau, we usually just omit the pairs of the I pairs, which is really nice. But our matrix is actually doing double duty because foremost, our matrix is this list of lists. But then also we tack on some extra data. We tack on this rows and columns. So there's list data and there's dictionary data. So when we specify I pairs, we're only looping over the list data. Right, so let me add that back. And I guess because each row is a vector, we don't actually need the I pairs. All right. I think the last one we'll do today is division. Well, let me take a pause here because we should probably like verify that the things that we've written actually work. And to do this, I need a helper function. Oh, but the helper function was in the matrix I just deleted. Oh, sorry, so I've written this like two-string method for matrices, and I'm not going to present it to you because it's like, it's just complicated and not worth it. But this is going to let us print out our matrices. Thank you, Porf. Yes, we will do matrix equality this time. Yeah, the last two we have really is division and equality. Sorry, one sec. Okay, so this is my two-string, and I'm not going to explain to you how it works, but it'll help us print our MHCs nicely. So let's actually just do that now. We'll require a matrix, so and let's create a matrix. So let's do, in the first row we'll do 1 0 0 0 1 0 0 0 1. All right, this is a very boring matrix, but let's print it out, and then maybe we'll make a more interesting matrix. Let's do 1 2 3 4 5 6 7 8 9. All right, so we'll print out two matrices. And let's do a plus b, we'll do a minus b, we'll do a times 5, 5 times a, and let's see what we get. Oh no, these icons always get me. Okay, well, we got what we wanted anyway. Did we get what we wanted? This didn't print, right? Oh no, that's because I messed up my empty constructor. Let's do that again. Oh, you're kidding me. Okay, let's see what we did wrong. Calls. Oh, did I use the wrong naming convention? Oh, no, I once again screwed up my matrix constructor. Sorry, so matrix.rows is rows, matrix.calls is calls. And now we should have a properly kitted out matrix. Okay. All right, very good. So what do we have? So we have 1 0 0. So we have our first matrix, 1 2 3 4 5 6. Good. And then we have the sum. So let's verify. So 1 plus 1 is 2. 2 3 4. Yeah, okay. This is good. We have our addition subtraction. We multiplied our first matrix by 5 on each side. All right. Okay, the suggestion in the chat, why not just fire matrix.new in the matrix.empty? Yeah, why not do that? Let's see. Oh, well, matrix.new, it takes in something, and then you clone that thing. So we would have to like, I mean, we basically have to do the same thing. Like we'd have to create our empty matrix, feed it into matrix.new, and then it'll clone it. Right, like the whole point of this function is just like allocate some new memory for a matrix. All right, and then JMK says, alternatively, you can make rows and columns a new index function. I'm gonna stop reading right there. That's too complicated, but you can do that, JMK. Okay, So we're almost there. We're almost to the finish line. 3 minutes left. Let's finish division and let's finish equality for board. So division, what's easier about division is that you can only divide on the right. So the matrix is definitely going to be on the left. The number is definitely going to be on the right. And let's make sure. So we'll assert. Oh, it looks like I've been, no, okay. All right, and then we need to define a new matrix. I could probably just copy and paste something. Okay, well, that came back to bite me really quickly. All right, matrix.rows, matrix.calls. We're going to loop through each row in the matrix. We're going to loop through each element in the rows, and then we're going to divide the ijth entry of the matrix by the scalar. And optionally, you could like assert that the scalar be non-zero. And you know what? Maybe we should do that. So we'll assert that the scalar is greater than 0. Yeah, why not? All right, so there's division, and then finally we'll do equality. Surely I can steal something here as well. Good, good. Don't need this. So we're going to loop through each of the entries, and so if the ijth entry of A is not equal to the ijth entry of B, then we'll just return false, that they were not equal. And otherwise, at the end, we'll return true. Let's make sure we didn't mess anything up. So do B over 10, and then how about print A is equal to, let's see, right, A is equal to B, and then we'll have some C that's just the same thing. Let's print B is equal to C. All right, let's see. So, yep, each of these got divided by 10, and then good. So A was not equal to B, and then B was equal to C. So there you have it. Now, last time we did our vector class on like just under 100 lines, so I'm curious. Okay, about 170. Fair enough. It's a little more complicated. Maybe if you take out the toString, it's a little less, but pretty good. And then next lecture, we're going to implement matrix multiplication and probably look at more cool pictures as we tend to do. So that is the end of Vector 101 Lecture 6. Thank you all for coming, and I'll hang around for questions now.